Hi, this is Lab 3 of Physics 2211. In this lab, we were given the scenario of a star orbiting a black hole and tasked with finding the mass of the black hole. To do this, we were given the positions of the star over a complete orbit and its velocity at each point. This is useful practice for us because we can find masses of other objects in similar scenarios, such as the discovery of a new black hole with objects orbiting it. If both objects are moving, then we will need the position and velocity data of both. Given the star's velocities, I calculated delta V between two consecutive points. I then multiplied that by the star's mass to find its change in momentum. The rate of this change has the same value as the net force on the star. In the scenario, the only force present was the gravitational force, so Fg equals Fnet. I made that substitution in the next equation and solved for the mass of the black hole, which is represented by either m1 or m2. I could also calculate the parallel and perpendicular components of the force using the following equations. These are the parts of the glow script code that I changed. On the left, I set some constants. Delta T is equal to 1 day in seconds. All of my calculations are in the code on the right, and in the bottom left is my code for the force vectors. They are all centered at the star's position, as that is the system. Here is the video of the orbit. The orange arrow represents the net force, the magenta one is the parallel component, and the cyan one is the perpendicular component. The model helps us to visualize all relevant values of the calculations. As you may have seen, the outputted mass of the black hole was not constant for each iteration. This is because my calculations assumed that the black hole did not move. This is a common simplification when one object has a much larger mass. According to Newton's third law, the force between two objects acts on both equally. However, if the objects have different masses, they will have different accelerations according to his second law. I found the average mass of the black hole to be 8.93013 times 10 to the 33rd kilograms. To find a more accurate mass in future calculations, I would need the black hole's position and velocity data so I could know the exact distances and forces between the objects. Gravitational force is inversely proportional to distance. This can be seen in the model. The net force and the net perpendicular force are very large when the star is close to the black hole, which results in a greater acceleration. On the contrary, Fnet parallel is so small that it sometimes cannot even be seen. The perpendicular component changes the star's direction. This is non-zero throughout the orbit because the star moves in an ellipse, so it is always changing direction. It is also generally towards the black hole. Fnet parallel controls the star's acceleration. The star speeds up going towards the black hole and slows down going away. The magenta arrow points in the same or opposite direction of motion depending on the sign of acceleration. Mathematically, force is the same as rate of change in momentum. However, they are different physical quantities. A force is an external push or pull on an object, which causes acceleration. Acceleration times mass is the change in momentum. This can also be thought in terms of motion. Every object has momentum, and after a force acts on that object, its momentum is different than before. This means that net force directly causes a change in momentum. Both quantities can be separated into parallel and perpendicular components. The parallel one is in the same direction as motion, and the perpendicular one is towards the center of the osculating circle of the turn. For force, these components may not actually exist. In the orbiting scenario, there was only one force and it was at an angle. However, the rate of change in momentum actually exists, and the components have the physical meanings mentioned before. Finally, if the black hole was replaced with another one but the star's motion did not change, then the new black hole must have the same mass as the old one. In the gravitational force equation, the only variables are the mass of the two objects and the distance between them. If the star's mass and the distance does not change, then the black hole's mass cannot change either. Thank you.